Here we have a reaction, a delta H standard, a delta S standard, and down here we're given a delta G standard. The quantity of heat really released when you use this many grams is the standard value adjusted for how many moles of reaction you run. So if you have 2 moles of this, you get to run the reaction 1 mole of times. If you have 4 moles of chemical, you only get to run the reaction 2 moles of times. So what we're going to do is convert to moles and say you get the reaction 1/2 as many times as this number of moles and multiplied by the delta H standard. And that will be the kilojoules per mole of chemical. Notice that it's per mole of chemical on the bottom there that you will get. Remember, we have delta G standard, and we're just going to put it in here. We know the temperature is 298 Kelvin. Remember to make this joules by multiplying by 1,000. Don't forget both negative signs. It's very easy to end up with 1 through carelessness, but we've all done it. And multiply and take inverse natural log. This has a justification using Gibbs free energy equation. I have another way. If delta H standard is a negative number, then the heat is coming out and it lives over here. If we increase the temperature, that's providing heat to the reaction, that will force it back left. Left is a less negative delta G standard number, less negative. If the reaction is being forced backward in the current conditions compared to the previous conditions, then delta G standard has got to become more positive. Or we could say if this is going up, then because this is a negative, right? This becomes more positive. And so this answer is becoming more positive as this we know is positive, it's going greater, greater, greater. On C, we're asked for the standard molar entropy for O2, and that might seem like that's maybe even impossible, but the standard delta S will be the standard entropy of the products minus the reactants, remembering that this is rated per mole of reactions run. When we run the reaction 1 mole of times, you need 2 of these and 1 of those and 2 of those. So what we'll get is the entropy times 2 minus this entropy times 2 minus this entropy times 1, and that's what we're solving for. So here's the product value times 2 minus one of the reactants value times 2 minus this distributes in the O2 value times 1, and we'll solve for the S standard O2 as X. The somewhat difficult thing to remember maybe about the bond energy calculations is that it's reactants minus products. We've said it so many times the other way around that I start to forget. The thing that gets me back on track is remembering that if you break a bond, you put energy in. If you form a bond, you get energy out. When we run this 1 mole of times, we're going to break 2 of these and 1 of those and form 2 of those, but we have to drill down a little farther. We're going to break 2 of these bonds, that's energy in, that's a positive value. 1 of these, that's energy in, that's a positive value. And the other trick to this that is very easy to forget is that the N is in the middle of 2 O's. So it's bonded once, twice, and then we have 2 of that molecule. So we're going to form 4 of those bonds and release that much energy, that value down below, 4 times as we create 2 molecules of this. So we'll take the delta H standard value from the very top and put it in here. Take double this, put it here. 1 times this, put it there. We're solving for this, so it's 4 of those. Remember that that's a negative because they're being formed and energy is coming out. Then we can subtract over, divide by -4, and we get our final value, and that is for NO2.